today we will have, okay, got it, good. Today we will have a little bit of maybe exotic topics. I assume you have talked about the most widely used evaluation semantics, which is call by value or also called strict evaluation semantics, which means that when you call a function with a set of arguments, the argument expressions are first evaluated, reduced to values, and then passed to the function. So with these values, the function body is executed. And that's why call by value, because we first reduce arguments to values and then start executing the body of the function. Today, I will talk about two alternative evaluation semantics. I will spend quite some time. Yeah. Where is the mouse? Sorry. Okay, so most of the time I will talk about lazy evaluation, and specifically as it occurs in one particular programming language, in the Haskell programming language. Then I will talk about the advantages of lazy evaluation, or advantages and disadvantages compared with strict evaluation. We'll talk a little bit about lazy evaluation and other language features, the interaction between them. And then I will just give a glimpse to this other alternative evaluation regime, which is called reactive evaluation. And next lecture will elaborate more on that one. So let me start with the question. Do you know languages that shortcut the evaluation of expressions? So lazy evaluation is basically about shortcutting the evaluation of expressions. Do you know languages that do such shortcuts? You can just turn the mic on and say something if you want, of course.
I have an idea.
Okay, go ahead.
So when we have something like Java, and we have an if statement, and we have an AND in that, we have
exactly.
A and B. B is only evaluated. Yes, exactly.
Exactly. So in many languages, we have this minimal evaluation of conditionals, which is very good to avoid expensive and or dangerous computations. And there are two examples in this slide. So in the first example, we have this if A and some function, my function B, and assuming that my functions may encode very expensive computations, we avoid calling it at all if A is false. And in the second example, we avoid doing something potentially dangerous, so calling a method on a variable B, which is null, which is not initialized. The idea of lazy evaluation is to generalize this shortcutting evaluation to the evaluation of function arguments. So not do only such shortcutting for conditionals, for in an if statement, but for any function. So the idea is that the arguments of functions are evaluated only when it is necessary to do so for the evaluation to continue. That is only if an argument's value is needed to compute the overall result of the function. And in Haskell, Haskell goes even further in the sense that this is true, this lazy evaluation of arguments also for built-in operators. For example, for the list constructor operator, which in Haskell is this column. So if you would run Haskell and you would execute this expression down here, which basically is a function application. So the first part of the expression defines a lambda x, which maps any argument x to 3, to a constant, and then we apply this function to the division of 7 by 0. In any widely spread language, like for example in Java, this will throw an exception, division by 0, because the argument to the function application will be evaluated first, and then we will get to this division of 7 by 0 and get an error back. In Haskell, we would get 3 because the argument of the function is not used at all in the function body. So the argument passed to the function in the application is not evaluated, so we never do this division by 0. Now, an argument can be used several times in the function body, which would result, if we did this lazy evaluation in a naive way, in the arguments being re-evaluated several times, each time they occur in the function body. And real-world languages avoid this by implementing lazy evaluation in a form that is called call by need. So we use memoization. Once an argument is evaluated, its value is stored, is memoized, and then this means that an argument is evaluated at most once. Now I will go a little bit through some Haskell constructs, like for example, function application, to show what the effect of this lazy evaluation is. Now, a function definition in Haskell looks like, as you see in this slide. So there are several so-called pattern matching cases. So we define pattern matching on the arguments of the function. And then we go through all of these cases, and the first one where the arguments match gets executed. Within a pattern matching case, there might be guarded branches. You could think of them like switch statements. There is a guard, and if the guard is true, the expression next to the guard on the right-hand side of the guard is evaluated. And in the definition of each guard or each pattern matching case, we can have local definitions like this where clause in the where clauses. We will see, I believe, an example. Let's see. So the function you see here has basically two pattern matching cases. The one where the arguments match are equal to P1, P2, Pk, or the other one where they are equal to Q1, Q2, and Qk. So correspondingly to this kind of template for function definitions, there are three aspects in evaluating a function application. So F applied to the arguments A1 to AK. The idea is that the arguments are evaluated only sufficiently to see whether they match the patterns in the function definition. So if the parameters match the first pattern, P1 to Pk, then the evaluation proceeds using this first branch. So the arguments are evaluated only so much that I can decide whether the pattern matches. And then I continue with the second pattern if it doesn't match, if the arguments do not match the first pattern, and so on. To give you an example, here in the top left, I still cannot use really my mouse, I don't know why. In the top left corner of the slides, you should see a function definition, F. The type of this function is, it expects two lists of integer values and returns an integer. So you see this arrow notation, this is a typing notation for functions. And then the function is defined in the body by three pattern matching cases. The first one says, if the first argument is the empty list, this is this squared brackets with nothing inside, then I immediately return 0. This is the case 1. the version F1. The second case says if the first argument is a list, a non-empty list. So what it says, this definition says it is an X and XS's. So there is at least one X, one element, and a list of following elements. But the second list is empty, then again, the result is 0. If both parameter lists are non-empty, so they have at least one element, then I just sum the first elements and return this as the result of the function. Now, let's assume that we call f with two lists, two equal lists. The first one is the interval 1 to 3, and the second one is the same because they are equal. So I will start checking whether the first case matches. For this, I need to kind of unfold a little bit the first list. I need to see whether it has at least one element. So I will need to extract the first element, 1. So to kind of distract the list into the first element, which is 1, and the rest, which is the interval 2 to 3. And then at this point, I see that the first parameter is not the empty list. So the first pattern doesn't match. I don't evaluate the first argument further, and I don't evaluate at all the second argument. I continue with the second pattern, which says that, which I mean, is triggered, is executed if the first argument has at least one element, which we know this is the case. But then we need to decide whether the second element is also empty. And for this, we need to kind of distract the list, to decompose it into the first element and the rest of the list. Again, we can do so. So at this point, once we have extracted the first element, one, we know that the second pattern doesn't match. We have to continue to the third case. And for this, we have done all evaluations that we need, because we know we only need the first elements of both lists, and we have extracted those two first elements, and we can compute x plus y at this point. The rest of the list of the both list arguments is not evaluated, no matter how big the lists are. The same thing with evaluation of guards. All right, here's another function which expects 3 parameters, all 3 of type int, and returns an int, basically the maximum of all 3 arguments. And for calculating the maximum, we have 3 cases, 3 pattern. We have one pattern matching case, but 3 guards. The first one checks whether m is bigger than n and bigger than p. The second one checks whether n is bigger than m and p. And then the third case is executed if none of the above guards is true. Now, when we start executing, let's say we call this function f with the expressions 2 plus 3, 4 minus 1, 3 plus 9. I mean, you can imagine that these expressions can be arbitrarily complex. Here they are relatively simple, that's just arithmetic expressions. So now I need to decide which guard is true. For this, I need to check whether m, 2 plus 3, is greater or equal n, 4 minus 1. And for this purpose, I need to evaluate both these arithmetic expressions resulting in 5 and 3. And then I can kind of evaluate this expression to true, because 5 is greater than 3. Then I need to continue the evaluation with the second part of the guard, checking whether 5 is greater than or equal than 3 plus 9, 12. I say this is false. But you see in this case that I have now evaluated m and n, and I store those. So this is basically the idea of this call by need. Once I evaluate argument expressions, I store them, I memorize them. I don't need to recompute them again when they appear later. Like in the second guard, we also have m and n. as part of the definition of the guard. Now we can reuse their values directly without recomputing them. So now I can see that the second guard is false because 3 is not greater or equal 5 and not greater or equal 12. So the guard or the case otherwise applies, and then we return the value of P, which we also have calculated. The idea is the same when we go into evaluating local definitions. So in this example, look at the where clause. We define a list, we give it a name and use it in the guard, in the definition of different guards. The execution with the lazy evaluation semantics unfolds here in a similar way as we have seen, so I will skip it, but you do have the slides will be made available so that you can go yourself through the different steps. Now, we talked about the lazy evaluation of function applications. Let me say 2 words about the semantics of evaluating built-in operators and other expressions. Boolean operators have this minimal evaluation semantics, as we also have in Java. Arithmetic operations, they vary depending on the operator. So plus needs both operands in order to evaluate. So we'll need to evaluate both arguments before computing the result of plus. Equality on lists returns false on comparing an empty list with a non-empty list without examining the non-empty list. Neither of the compounds of the non-empty list, neither the first element nor the rest of the list. If then else is evaluated like guards, cases, which is another expression, another construct in Haskell, is evaluated like a pattern match, and let is evaluated like a where. Now, I would move to the second block of the lecture and talk about advantages of lazy evaluation. In case you have questions about the part that we just went through, please, you can raise them now. Any questions? Doesn't seem to be the case. So I will continue a little bit further. So what are the advantages of lazy evaluation? Well, first of all, we have the fewest number of expressions evaluated. So any expression in a program is evaluated only if it is necessary to do so, and only once. So this is the minimal number of evaluations. Another interesting advantage is that we can define, we can encode control structures like if then else, as if they were regular functions rather than having them as built-in primitives. And I will explain a bit what I mean by this. The third advantage is that we can define infinite data structures, and I will elaborate on this too. And the fourth is the thing that I will elaborate also on, which is modular process-style program organization. It allows, so this lazy evaluation enables us a modular program structure without sacrificing efficiency. We will come to this. Let's start first with control structures as regular structures, regular functions. So if conditionals can be seen as operators that make a choice based on the value of the condition C. Now, think of it as if the choice was made by the Boolean values. So one could think of the Boolean values, true and false, as functions that select between two alternative expressions to evaluate, which are passed to them as parameters, the if true expression and the if false expression. So in the yellow box, you see a template Scala definition of the functions true and false. Both are parameterized by the type T, which is the type of both if true and if false expressions that are passed as parameters to true and false function. And each of these two functions return a value of type T because they select between executing the if true or the if false parameter expression. And there are languages, I mean, kind of exotic languages. I guess none of you have ever heard about Smalltalk, but it's one of the first and most powerful object-oriented languages, which had very amazing features already in the 80s. And there, for example, Boolean is indeed a class, and it's the superclass of true and false, and true and false have indeed such functions as selecting what expression to execute. So the definition of the functions true and false is actually very simple. They have these two parameters, if true and if false, and true executes if true and false executes the if false parameter and ignores the other. Now, given this definition of true or false, do you think that these definitions, these functions, are really a replacement for the conditional if? And to make the question more specific, if you look at the examples in the kind of bottom left corner, the print line with the application of true to the expression 3 + 4 and 7 divided by 0, what do you think will be printed?
Svenja, you don't have to raise your hand. You can unmute and just.
Yeah, just.
So about the evaluation, the first statement would print 3 + 4, so 7, and the second would print 12, but the third one would throw an exception, I think, because this is Scala, and Scala does not by default have lazy evaluation of function arguments. So 7/0 is evaluated and it does not work.
Correct.
So
perfect.
In principle, in a lazy language, this should be okay as an if, but not in a strict language.
Exactly. Perfect answer. So we have to be careful when we say we model conditionals as functions instead of built-in operators. This is a valid statement to make in languages that have lazy evaluation or call by name, but not in languages where our language in which we define true and false does not have lazy evaluation by default, which is the case with Scala, as Svenja just said. Okay, let me move on with explaining what I mean by lazy evaluation enables us to define infinite data structures. Recall that I mentioned that in Haskell, also the built-in operators in the language, like the list constructor operator, are also lazy evaluated. And this is exactly the point or the key to enabling us to define infinite or finite but very, very large data structures, of which only as much is actually produced as actually examined by customers. So for example, one could ask, how would you construct an infinite list of ones? I mean, this is kind of a toy, nice example, not much practical use of it, but nevertheless, here is the definition in Haskell. You just write this recursive definition. The infinite list of ones consists of 1, the first element being 1, and the rest of the list, which is again defined by our definition of ones. In a language like Java or Scala, you cannot write such a very declarative definition of an infinite list of ones, which says I have a 1 and then as many ones as I need, because we have this recursive definition. So when I try to evaluate the ones on the right-hand side of the equal sign, it will say it's not defined. But in Haskell, the second argument to the column, to the list constructor operator, is not evaluated until necessary. So when it does, there is a definition available. We know that there is a 1 followed by more ones. So the result of the definition, the ones, is actually a promise to construct an infinite list of as many ones as ever needed. So only the act of examining the list actually constructs a prefix of it, as many ones as are needed. So extracting, let's assume, that we have this function take. It's defined with the type int, and a list of a's returns a list of a's. So the function takes 2 arguments, an integer and a list of arbitrary elements. A is a type parameter. This is like generics in Java, right? So we know that we have a list of some type A. And given this int and the list, we will get back a list with elements of the same type as the argument list. Take is defined with these 3 pattern matching cases. So take with the second argument being an empty list. I don't care, the underscore says I don't care about the first parameter. If the second parameter is empty, I know immediately the answer is the empty list. Similarly, if the first argument is a 0, so we take 0 elements from the list, I don't care about looking at the second argument of the function, at the list per argument. I can immediately return the empty list. Now, the third case is a little bit more interesting. So it says for any number, for any integer n, and any non-empty list, which has 2 parts, the first element x and the rest of the list xs, I know that I define the result recursively by saying this is the list that consists of x as the first element and the result of calling take with n-1 and the rest of the original list as parameters. So if I call this function take with 4 and 1s as parameters, I will get back 4 1s. So this is the idea of the list. We only kind of produce prefixes of the infinite list once, as many ones as they are needed by take, as the take consumes. I can go on and in a similar way define the infinite list of integers. How can I do this? Okay, in Haskell and in many other functional programming languages, but also in Scala, there is this zip function. In Haskell, it's called zip with. The function takes a binary function f as a parameter and 2 lists, L1 and L2, and constructs a new list by applying the function parameter f to the elements of the input lists with the same index in a pairwise way. So in Haskell and many other functional programming languages, also in Scala, which is kind of a mixture of functional and object-oriented programming language, we have higher order functions, so functions that take other functions as a parameter. Zip with is such a function. It expects f, another function, as a parameter. So how does zip with works? Given if I have any F and the second list is empty, or any of the input list is empty, these are the first two pattern matching cases, I know that the result is the empty list. The third case says for any F and any two non-empty lists, I apply F to A and B to the first element, to the respective first elements, and then concatenate this with the result of applying zip with the same F function parameter, but to the rest lists of A, B, A, S, and BS. The result is concatenating with the result of applying F to A and B. I can use this function now to define the infinite list of integers. So here is one definition. Integers are defined as the list that starts with 1 and has a rest part, which is defined by applying zip with the parameters, the plus operator as the function, and the two lists 1 and integers. And you see down here that if you put the integers and the ones on top of each other, then basically with the operator plus, we sum pairwise the elements of these two infinite lists, and we get basically 2, 3, 4, and so on, which is the rest of integers. The first element is given to be 1. And even if this definition is kind of recursive, I don't have a problem, because the arguments to the constructor operator of lists are only lazily evaluated. We kind of unfold this infinite list only as much as is needed. In this case, when we call take with the parameter 2 and integers, only 1 and 2 will be produced. So the definition of integers is again a promise to produce as many integers as are taken or are consumed by some client. Okay, and in the slides you have also a more complicated example, the definition of Fibonacci numbers by using these features of the lazy evaluation. I have skipped it for sake of time, and we'll talk a little bit of why these infinite data structures are interesting. Like we talked about very toy examples here, but there are real applications, there is a real usage of these infinite data structures. When we have an infinite version of a program, this can be, when we are able to define infinite versions of a program or of a data structure, these can be more abstract and hence simpler to write. I mean, you can think of it by the analogy with virtual memory. Predicting the amount of memory that a program might need could be possible. Nevertheless, it is very tiresome, and it will certainly pollute the program with unnecessary infrastructural code trying to track how much memory the program needs. With virtual memory, such a prediction is made unnecessary. It doesn't need to be done at the application level, at the program level. It's the language machinery, the operating system that takes care of predicting how much memory it's needed. For the program, it looks like there is a unlimited space up to the maximum address space, and the programmer is relieved from tasks related to memory management, which not only makes the job for the programmer easier, more importantly, the design of the programs is cleaner, higher level, easier to understand and follow, and also to evolve, less prone to errors. I mean, this paper that I'm citing here, lazy versus strict evaluation, this is kind of June 69, so it's pretty old. I guess some of you, or all of you, I don't know, were not born. But to give you just an idea of a real usage of infinite data structures in industry, think about CAD systems. They typically show or manipulate designs that are represented by constructing trees or graphs of parts which may be very big and need to be displayed. So in order for performance reasons, we want to minimize the amount of the graph that is constructed, especially because someone that is working with the graph will, at a certain point in time, will not need the entire graph. It's working anyway with some part of the graph. And here, lazy evaluation can help to display only that part of the graph and construct the rest of the graph only if needed or as it is needed. And there is also applications in expert systems working with very big database systems. And lazy evaluation is, in this case, essential, for example, to manage the interaction with the database, which returns potentially enormous data structures, but only as much is shown as it is being consumed by the user or by some other program that works with the database. Now, this was the second advantage, right? The infinite data structures, the ability to define infinite data structures in a very declarative way. The next advantage of lazy evaluation is that it enables modularity. What do I mean? What I mean is that we can construct software by just plug and play reusable building blocks for different stages of the process. And here, this is illustrated by the example of defining a function called sum of even fibs n, which basically takes the list of Fibonacci numbers, assuming, I mean, there is this fibs is defined somewhere, returns the list of Fibonacci numbers. We take n of them as the parameter n. We filter to get only the even fibs, and then we sum this even fibs. You see here, you don't need to go into the details, but there is a definition for summing elements of a list. There is a definition for filtering the elements of a list according to whether the elements are even or not even, and the take we have seen before. So there are these three functions which we can reuse. We plug and play them together to define the sum of even fibs. And we could go even further. We don't need to define sum. We can use existing functions or existing operators like map and fold or filter. These are typically predefined operators in functional programming languages and also in Scala. We can use them. Sum is basically a fold which applies the plus operator to successfully to the elements of the list. And filter even, we don't need to define, we can pass the predicate even to as a parameter to the predefined operator filter. So basically, if we want to define the sum of even fibs, we could plug and play these building blocks, enumerate all numbers, apply fib to each of the numbers to produce the list of all fibs. We filter them with the predicate even or not, and then the result is to the result list we apply fold starting with the element 0, initializing the aggregation with 0, and then using plus to aggregate all the elements in the list. So I have written here, this is reuse at its best. So fold, filter, map, and enumerate could be thought of as being, I mean, they are built-in predefined operators. I can take them from the shelf, put them together, and define new functionality. Now, the question is, do you see any problem with organizing our computations in such a way, especially in an eager or strict evaluation language? Anyone that has an idea wants to say something about this, and whether we have the same problem in Haskell or in any other language with lazy evaluation. I mean, if we did this plugging in a language with strict evaluation, we call by value, we risk of constructing, in the worst case, the list of all these numbers that we enumerate 4 times. So I create a list by enumerating our numbers. I pass it to the map. Map will return a list of the same size. I pass this list to filter. Filter might, depending on the predicate, can return a list of the same size. And then final default reduces the list to a number. But so we produce several auxiliary data structures in between these building blocks. In Haskell, we don't need to, because of the lazy evaluation. So the enumerate component will produce as many numbers as map requests from it. And map will produce as many numbers as filter requests or consumes from map, and so on and so forth. So lazy evaluation help us avoiding to have to produce auxiliary structures. And I will skip this part and move on to kind of summarizing this part about modularity. So to improve productivity, programming languages must support modular software construction. But just having scoping rules and mechanisms for separate compilations are not enough. Modularity is more than just having support for defining modules. As important as the ability to decompose a problem into parts is the other direction, the ability to glue solutions together. We need to have powerful glue mechanisms for separated parts. And the news here is that Haskell, or in general languages with first-class functions and lazy evaluations, provide exactly these 2 powerful kinds of glue. We can compose functions together by applying one function to another, and lazy evaluation helps with avoiding to have to execute the functions completely, produce complete results before I execute the next function in the composition. So this way I can define smaller and more general modules, and which can be reused widely. And this facilitates programming in the form of plug-and-play components. Now, this sounds all very good. What's the downsides? So how does lazy evaluation react or interact with other language features? Or to put the question differently, one might wonder, why do we basically mostly have languages with strict evaluation? All languages, object-oriented languages that we know, like Java, Scala, C++, functional programming languages like Scheme, Racket, ML, they all have, by default, an eager evaluation regime. What do you think is the reason?
So the first idea that comes to mind, especially for like Java or C++ or anything imperative, is that you have side effects. And if you have something that has side effects, then you can't do this lazy evaluation, because the program depends on the exact evaluation of functions in the correct order. But with lazy evaluation, this does not work. And in Haskell, of course, you have, well, a lot of pure functions.
That's a great answer. Before getting into, I will come to this answer, to exactly this answer that you gave. But I would guess that many people think programming in such a higher level language with higher level constructs like first class functions are functions as values that can pass around as parameters for other functions, and laziness are less efficient. And there is some effect of laziness on the efficiency. Why? I mean, I've skipped a whole block of the lecture talking about how to implement lazy evaluation. For those of you who might be interested to look at, you will have the slides, you can go through them. But the key idea is that I need to create and maintain so-called expression closures. You have probably talked about function closures. An expression closure is basically a data structure where I store an expression. I store the environment at the time of the expression definition, so the binding of variables to values at that point. And eventually also, I mean, we have caching, we have memoization. Also, if the expression is evaluated, then I'll need to store that value to be reused in further usages of the expression. So an argument expression is represented in those languages with lazy evaluation as a data structure. The data structures contain the expression itself, the environment that binds variables that might appear free in the expression to values, plus potentially the already evaluated or the value of the expression if the expression is evaluated already, plus a tag maybe showing the expression is evaluated or not yet. And this one could think this may contribute to increased execution overhead. There is some space complexity, which is additional. I need extra cells to hold these data structures I talked about. There might be some time, there is some time complexity because I need some time to create the closure. I need some time to invoke the closure, the expression closure when I really need the value to force, so to say, the evaluation. And I might need some more time to update the closure when I have a computed value, to store the computed value, and so on and so forth. And especially, we come to the point of side effects. Caching implies that I don't have side effects. And we will come to explain why side effects are a problem when we use caching. But the lack of side effects may itself be costly, because it may require us, since we don't have mutable states, side effects, lack of side effects means we have a pure language, we have no mutable state. Everything has to be modeled as a function and function composition, which might require the creation of these intermediate tuple lists and data structures, which I talked about. Now, in a language with side effects like Java, for example, we cannot cache expressions, because here's the example. We have this expression in the code. We define an account, and then we call get balance on that account object ACC twice. But we cannot cache the result of the first call and reuse this result in the second call, because in between these two call expressions, we can have accesses to account via either other pointers or via ACC. And then it's invalid to reuse the cached value in the second appearance of this expression. So any language that caches computations, hence also all languages that do call by need, lazy evaluation, is making the assumption that an expression computes to the same value every time it evaluates. This is also called referential transparency. It has great features because it simplifies reasoning about programs. So to understand a program, I don't need to understand and be aware of the global control flow of the program. I can apply equational reasoning, the process of reduction, which is already well known from high school algebra. Haskell can cache values because Haskell is free of explicit side effect operations, so it's a purely functional language. As I said, programmers perform all computations by composing functions. So to recap, these expression closures, E-closures called on this slide, and the lack of side effects may be expensive. Everybody would think they are expensive, but keep in mind when people jump and tell you immediately when you present or you say you like a high level language like Haskell, and you get immediately this kind of feedback, oh, okay, this is certainly not efficient enough. Keep in mind that compilers can be very powerful and apply sophisticated optimization techniques to reduce this overhead or to eliminate the overhead, the apparent overhead. And this is the case indeed with Haskell. So it applies very sophisticated optimization techniques. It analyzes when actually the compiler can evaluate the expressions, can be strict. And there are efficient implementations of closures and expression closures and so on and so forth. And the other way around, the lack of side effects, while I said might be expensive, especially in a language that doesn't have lazy evaluation, because I have to define intermediate structures or to create intermediate state and pass this intermediate state around. But the lack of side effects enables Haskell compilers to perform optimizations that are not available to traditional compilers, to compilers of languages that have side effects. So to summarize, efficiency may not be the reason. It's not the real reason, but exactly what we heard before from Svenja, the problem is that there is a conflict, so to say, between laziness and the need to exactly determine the execution order of the instructions in the program. This is not a problem in a purely functional language, which has no side effects, because in such languages, one is concerned with the results. It's like doing math and not with how the results are computed. We declare what the results are based on some other values and expressions that we have, and we are not concerned about how they are actually computed. And lazy evaluation is attractive in this case, especially given that its termination properties are better than compared to call by value. But programs in a lazy language are not islands. What does it mean? So programs eventually interact with the outside world, which itself has inherent or true side effects. If some events happen, this is an effect. I cannot hide it. It's there. My program has to interact with these effects. And that complicates the matter, which is kind of expressed here in the text in orange, saying that any language with side effects must have a transparent and easy to understand order of the evaluation. And with lazy evaluation, we actually don't know exactly the order of the evaluation. It is the compiler that, I mean, as the execution unfolds, we know actually the order. I mean, the compiler, the execution engine of the language knows the order in which things are evaluated by, but we as programmers cannot actually tell by looking at the program in which order the instructions will be executed. And this is kind of counterintuitive, does not mix well with exceptions, concurrency, input, output. And that's exactly the reason that Svenja told us why lazy evaluation and laziness is not widely used in mainstream programming languages. So the problem is that languages with lazy evaluation need mechanisms for sequencing expressions, the evaluation of the expressions without violating this referential transparency. And Haskell has such mechanisms. They are called monads. and there are other languages that have other mechanisms. The thing is that these are pretty sophisticated mechanisms, so maybe not that easy to use and understand for the average programmer. They also contradict the traditional stop, examine, continue model of debugging. Of course, Haskell has debugging techniques, but they need a shift in the way we think about debugging. And that's the reason why lazy evaluation actually is not further or more spread, more used in mainstream programming languages. But to conclude, you should keep in mind there are pros and cons. There is no black and white. Both strict and lazy evaluation have their advantages and disadvantages. We talked about them. We talked about the advantages of lazy evaluation. And in the past few slides, I talked a bit about disadvantages, right? This kind of complicating reasoning about the order in which, or obscuring the order in which the instructions are actually executed. And some applications use languages with one or the other evaluation regime because the respective regimes are essential for them. So I talked about this example of the CAD or big databases that are examined only partially. These are use cases where lazy evaluation makes a lot of sense. And this thing of both of them having advantages of disadvantages, the reason why we see the gap between languages with lazy or strict evaluation getting narrow, more and more narrow, in the sense that most lazy languages have constructs for enforcing the evaluation, enforcing the order of the evaluation for strict evaluation. In Haskell, I mentioned MODAT, but there is also an operator called sequence, which kind of prescribes the order in which instructions have to be evaluated. Let the programmer prescribe this order, tell the machine in which order the instructions should be executed. The other way around, many strict languages have support for lazy evaluation in one form or the other. So I started the lecture by talking about shortcut evaluation of conditionals, for example, minimal evaluation of conditionals. This is very widely spread in many languages. In addition, some languages provide special forms for delaying the execution of selected computations, which are marked as such. In Scala, for example, you can mark a computation, an expression with the keyword lazy, and this ensures that Scala will execute this expression in a lazy way. Okay. This is basically what I wanted to tell you about lazy evaluation. And I'm about to jump to the last block of this lecture, talking about reactive evaluation. Before doing so, I'll be happy to take questions regarding lazy evaluation, if there are any questions.
So we see in most like modern languages like Java that lazy evaluation is also like implemented there with streams and stuff. Do you see more of an integration of lazy in languages like Java or anything without having to construct like expensive streams?
I mean, as I told you, I mean, you say expensive streams. They don't have to be expensive. So Haskell tells us that lazy evaluation does not have to be expensive. In that sense, I think there is no conflict. So we can have lazy evaluation in strict languages without paying too much overhead for it. I guess, I mean, the streams are probably not yet optimized enough in Java. But there are easy, ready to use optimization techniques from Haskell, for example.
Yes. So the expensive was not meant like as in general, lazy does not have to be expensive, but like Java streams do produce a lot of overhead if you use them.
Yeah, but there is a lot, in research, there is a lot of work on stream fusion on optimization mechanisms for streams. They just haven't made their way to practical language design, but eventually they may. So that's the story. So everybody talks about Rust nowadays with the ownership features, ownership type system. Ownership type systems and borrowing disciplines have been the subject of research for years. At least 10 years, as far as I can think back. And they were considered rather exotic, but then you get Mozilla that understands what these features are good for and puts them in a real language. And that's how things evolve in the programming languages design and implementation space.
So if I may add something.
Ragnar, you are there. Yes.
I am here. So hi, for the rest of you, I'm not quite a student anymore, so I have lots of opinions on these things. First on, I think like this general question of, will we have more lazy evaluation in current languages? As far as I can see it, all currently used languages support to implement lazy evaluation in some form, because you can always emulate lazy evaluation if you have closures, or at least have functions and can create your own objects. You can always emulate kind of the efficiency behaviors such that you can compose things. It will often look a lot worse than in Haskell. You won't have these nice short features because everything is built into a language. Java Streams was an interesting example, because there they try to get this laziness, but everything has more boilerplate than in Haskell, for example. Right? But in general, you get these abstractions. They may be complicated, but you have them. So lazy evaluation is the thing that in a lot of complicated applications, you find it. You don't necessarily see it very obviously, but applications always have things they don't want to execute right now. They delay to later. They delay to when someone wants to read it. Databases, for example, they do this all the time for efficiency. It's one of the fundamental things in databases, that you have these views that are only computed when they are accessed. These things are everywhere. You just have to know how to look for them. The second part is this: why is there so much overhead, for example, in Java streams? Or can we have like super efficient, low overhead evaluation? The answer to that is yes and no. The general problem is that the nicer your abstractions are, the more you can compose them, the harder it is to optimize for the one special case that right now is the thing that you need to be fast, because that may be different for every application, for every composition, and it's not always super obvious from the abstractions when you need what. There's something that often can be improved for common scenarios. For example, the Java streams have specializations for if you have a stream of ints, because Java is a language where primitives and non-primitives types have very different performance characteristics. So they try to also optimize streams for the primitive types. This doesn't always quite work for the wrong reasons. But when it works, Java streams actually can be very efficient. You sometimes have to understand the execution model. You sometimes have to use them in a certain way, but there's no theoretical reason why these things should be more expensive than just writing a loop in the case that they do the same execution. then again, there are other cases where they do much more and they have to be more expensive because that's just the program logic. And the issue is kind of that they look superficially very similar in the case where they're expensive and where they're not expensive. And this makes it sometimes hard for programmers to be like, well, which part of my code is the expensive one, right? Because everything looks simple, but some of these simple cases are expensive and some are not. This tends to be more of the issue with performance evaluation. So it's then a question of, should expensive things look very expensive? Should they be hard to write down? And this really depends on what you optimize for. Do you really need every last bit of performance, or is it more desirable to have most cases be performant and then everything be simple to write? But now I've been rambling on too long. I hope that adds a bit.
That's okay.
Maybe I also want to add a small thing for the students here. So what Ragnar mentioned about emulating lazy evaluation, all of you have your language built, you have your interpreter, you also have pure functions right now with the last exercise. So I'm not going to make it mandatory, but it would be an interesting exercise for you to try out to see if you can implement a form of lazy evaluation in your existing language, especially since you have pure functions. So I'm looking forward to seeing some of you or all of you implement some form of lazy evaluation.
And you can get inspired by this item in the middle, implementing lazy evaluation. So in the slides that will be made available, you can find enough hints as how the lazy evaluation is typically implemented in languages with lazy evaluation. To add a little bit to what Ragnar said, this is kind of, in computer science, we also talk about this one size fits all, right? So Haskell enforces lazy evaluation to everything and then has very sophisticated optimization techniques and this monads to cope with side effects without sacrificing the referential transparency. And the opposite is languages like Scala, which most of the time have strict evaluation, but then enable the programmer to decide where it's worth or he or she needs. I mean, the application semantics are better fitted by lazy evaluation. Same thing with Rust, right? So the core language enforces strict ownership on values, but then programmers have the possibility to use the unsafe feature for cases where they really need to do very low-level programming. But this is supported in a much better way than in C, which has no control over what the programmers do with unsafe. In Haskell and in Rust, the assumption is that unsafe is used in libraries which encapsulate the feature enough so that it doesn't affect the rest, the pure core of the language. Okay, but let me move on and give you a glimpse of this second exotic kind of evaluation semantics. And Ragnar, which you heard explaining his thoughts, will continue with it in the next lecture. Okay, so I'm saying most of today's applications are interactive and event or data driven. What are most of today's applications? They are collaborative applications, things like Google Docs and Slack and Trello. I mean, they enable people distributed in time and space to collaborate with each other. There is all these social apps like messengers, chatting, there is gaming, collaborative gaming, there is the whole data economy. So very often computations in this kind of application space are driven not by the order of the instructions in the program, but by external stimuli. So the world is in control of the execution order and not the program. Now, how do we typically model interactive data and event-driven applications today? Well, we use callbacks. You could think of callbacks as a workaround to reconcile the mismatching order between external stimuli when they arrive, event and data arrival from the external world, and the order of the execution of the program. So what we do, we attach to each event a callback that once the event occurs, this callback, which is attached to it, is executed. And what the callback does is basically say, refresh, update, modify a web page appearance, which contains also the click me button. On the right-hand side, you see I have a button, click me, which creates an event, which causes a piece of code to run, the callback, and the callback has some effects on the appearance of the page. Actually, what I need to do here is to say that there is a relationship there is a dependency between the event, click me, and the appearance of the page, of the web page. Or there is a dependency between new data arriving and some plots, displaying some statistics about the data. And since our applications nowadays are very interactive and collaborative data and event-driven, we see these callbacks everywhere. But the problem is that they are kind of hell. I mean, you might have heard this kind of term, the callback hell. What does it mean? It means that programs that use callbacks tend to have very complicated, complex designs that are hard to understand, that have hard to follow side effects. Why is this? Well, first of all, as I said, I need to manage somehow the dependency between an event and computations that depend on that event or on some data that arrive from the external world. But since our standard mainstream languages do not support managing some dependencies by design, we will have to do so in the application code. What does it mean? Well, we have to implement callback interfaces, we have to implement registries for the callbacks, and we have to manage their life cycle as part of the application code. Also, some conceptually coherent logic, like whenever an event occurs, display should be refreshed, is split across several callbacks that have to coordinate their execution by mutating variables, which are broadly scoped, meaning they are have global scope. And this leads to side effects that are hard to follow. So to summarize, the statement I'm making here is that this reaction management is something that needs to be reevaluated whenever something else happened, which ideally would be part of the language design, would be a language feature, is not, and it has to be implemented by the application developer and obscures the application logic. To make you feel this, I have a incomplete piece of code here on this slide, and I'll give you 1 minute to think about what the code eventually does. And it's kind of pseudo Scala, if you want. It starts, I can start walking you through the code. So we first define 3 variables, hour, day, week. All of them have the type int and are initialized with 0. Then we declare a value of type event. Okay, so that's why I said it's a pseudo Scala. It's a Scala that has support for first-class events. Tick, the event tick exposes values of type unit, so void. And then we define two more events, new day and new week. Both do not expose values, basically. Their type is unit. And they are defined by composing the event tick, respectively, with two different predicates. The first one, the first predicate is a Scala function. It expects 0 parameters, and it's basically defined by the predicate returns true if hour is equal to 0. The second predicate returns true when day equals 0. And in the lower part of the code, you see these plus equal operators, which attach to all three events one callback. The first callback attached to tick changes the variable hour. So every time a tick occurs, the event tick is triggered by the operating system, let's put it this way. The callback associated with tick will execute, which changes the globally scoped variable hour, which may cause the predicate in the definition of the event new day to become true, hour to become 0, which, if this is the case, will trigger the event new day, which in turn will cause the attached callback to it to execute, which changes the variable day, which may cause the callback at the definition of the predicate in the definition of new week to become true. So new week to be triggered, which in turn causes the callback attached to new week to be executed, which may change again some global variable. So you see there are three callbacks, and they coordinate their execution via mutating variables, which are broadly scoped. So they are kind of global in this small piece of program. And you see that the control flow gets very complicated and hard to follow, because there is this conflict between the time when events arrive and the order of the instructions in the program. There is a question.
Yeah, excuse me, I would like to know what's the functionality of that modulus here.
Yeah, I will come to it in 2 slides.
Ah, sorry, okay.
No problem. So, I mean, this, yeah, shouldn't go back. But what I'm saying is this ends up being very complicated for a very simple functionality. Maybe I can say what it is. It's basically we are defining the meaning of day depending on how many ticks are triggered by the operating system. Then we use the definition of tick, or we could use the definition of day to define when a week ends, and then we can use weeks to define what a month is, and so on and so forth. I will come to it. But even this very simple functionality actually requires very complex control flow, which is, can lead to hard to follow side effects, which are prone to errors. And in fact, this is not hypothetical or theoretical. There have been, there is a study here, but I guess there are many more. There was a talk by someone from Adobe kind of stating that 1/3 of the code in their desktop applications is devoted to event handling, and half of the bugs reported during a product life cycle exist exactly in this code. So it seems like, a lot of code is needed for event handling, and this code is very error prone. And you ask, what does this code actually do? Ignore for the moment this keywords signal in the code, but basically it's saying, what is the definition of an hour? So I have a new hour, defined by, the hour changes when tick changes by the definition given there. The same thing, the value of a day, which day I am in, changes by the definition on the right-hand side, which depends on tick, and the same thing with week. So we basically wanted to express some logical relationship between ticks happening and the values for the actual hour, the actual day, the actual week. But in order to do so, we couldn't write these relationships as we do here in a very declarative way. We had to use all these callbacks that coordinated with each other. The code that you see here is written in a language that supports what I call, or what is called, reactive evaluation. Such languages have so-called signals as their first-class constructs. These are time-changing values, values that change continuously with time. Whenever other values, they depend on change, or events they depend on happen. And they do so, they bring their value up to date automatically. There is no need for me in the application code to make sure that the values are brought up to date. And something seems to be wrong with my, yeah. So you could think of these signals essentially as functions with a new kind of evaluation semantics. So we have talked about eager evaluation. We talked today a lot about lazy evaluation. And you can think of reactive evaluation in terms of arguments being evaluated as often as necessary. And then the entire corresponding function is also evaluated with them. Yeah, think about functions that automatically execute. I don't need to, when I have new values for the inputs, I don't need to recall the function to get a new result. The function is, or evaluates itself, if you want, it's self-evaluating every time input changes. Do you know software, kind of a software system with built-in reactive evaluation semantics? What comes to mind, or does anything come to your mind? Okay, Excel sheets, right? You define, you can define very complex formulas in an Excel sheet. You can even define plots that kind of display the status of the data. And the complex formulas or the plots, they depend on Excel, or on the values of certain cells in the Excel sheet. But when we define a formula, we just declare the formula and its dependencies on other cells. And then whenever I change a cell, any formula cell that depends on that change cell will be brought up to date automatically. The Excel machinery does it for me to keep track of the relationships between different cells and manage these dependencies and propagate changes as they are needed. So every time the cells that serve as an input to some formula cell need to change, they are changed, and also all formulas that depend on them, functions that use them as input parameters, are reevaluated automatically. Now, do you know programming language with built-in reactive evaluation semantics? I guess you don't. There aren't many or any mainstream languages that support the reactive evaluation semantics. But we have worked on such a language in the last, I don't know, almost 10 years probably. The language is called ReScala for reactive Scala. So the language is implemented actually as a library in Scala, but it feels like a real language. And Ragnar, that you heard the voice a couple of minutes ago, will introduce you next time into the details of ReScala. for me, the journey today ends here. And I certainly will attend the next talk on Rescala and see how, yeah, be very curious about your feedback on it. Thank you. Any questions at this point?
Sorry, I was muting. So thank you. And any questions?
Okay. I mean, we can also have a short session, question session at the beginning of the next lecture if there is need for doing so.
And as always, you can also collect it in Moodle, whatever you have. I'll also put up the recording once it's done processing.
Okay. Thank you very much. Have a nice afternoon and see you next Wednesday.
Maybe it's a short organizational injection. So the plan for the next lecture will be that I will pre-record a video of a deep dive into Rescala, demonstrating on a short case study, like the features, how to implement, how to use it, what the advantages are, and so on. This will be a video because so you can, skip over